All right, ladies and gentlemen, welcome to another tutorial video. This video will show something really cool. So this video is actually going to show us how to analyze polynomials using derivatives. So this is a concept that's taken from a part of mathematics called calculus, but we can use a very simple case of the derivative in Algebra 1 to look at our quadratic functions. And the key thing that we're going to analyze in our polynomials that we look at, in this case quadratics, by taking the derivative, is how the slope of a derivative line changes as you move along the x-axis. So let's get into that and see what it looks like in practice using an example. Okay, clear the work surface off. Let us take the example and show you what these questions kind of look like. Here's an example question, and this is how it will present in a math class. Example: what is the rate of change of the function what is the rate of change of the function f of x equals x squared when x equals 2, when x equals -3, and when x equals 0. So we're asking kind of three separate little questions there. Rate of change means slope. So what is the slope of the function x squared when x is 2, -3, and 0? Right? So that's our job. It's useful here to make clear why it is important for us to be able to do this. It's useful to compare two graphs. So I want to use a piece of scratch paper for that because I don't want to mess up the work surface. Let me just show you two different graphs here. So this graph right here is going to show a linear equation. Right, so here's a linear equation graphed. You see, it's a straight line. Everywhere along this line, the slope is identical. Right here, the slope, different y values, different x values, but the slope doesn't change. As we move along the x-axis, the slope stays constant. Do you see that? That's why we're able to plot these in using rise over run. It's easy. But many of you have noticed that when we're looking at quadratic functions, like here's an example of a quadratic function. When we're looking at a quadratic function, let's plot one in maybe that looks like this. There's a quadratic function plotted in. As you move along the x-axis, all right, the slope changes. And what we can do to kind of see that visually is to come in here with maybe this orange pencil and say, what is the slope when we're over here? So when x is negative over in this area. So if this is my x value, and I go up and hit the line from that x value, what's happening to the slope? Well, is the slope negative or positive right here? That's a question. Well, if you bring your ruler up here and draw a tangent line that kind of bumps up against the quadratic function, you would draw a line that looks like that, and they touch right there. So the slope is negative, and it's really steep, okay? Now let's move a little bit closer to the vertex of the quadratic. Let's move over here. So how about when we're at 0? Okay, so this is our new x value. Well, if we go down to the quadratic, now we notice that in order for me to bring my ruler in here, I can't make it as steep as that line. The game is you cannot cut through with your ruler. You can't cut through the equation. So you've got to kind of look what you got to do. As you move to the right and you keep your ruler underneath this function, you have to turn it. So do you see the slope is getting less and less steep? Now I get here and my slope is still negative, but it's less steep. Do you see how I did that? Now at some point, the slope is going to be absolutely 0. And where would that occur? Some of you already see where it would occur. It's at the vertex of the function. So whatever this value is, this is my new value. Okay, I'm going to go down to where the x intercepts that quadratic function, and now I have to, the only thing I can do is draw a perfectly horizontal line. Okay, so here for a perfectly horizontal line, the slope is 0. Okay, so we went from a big negative slope to a shallow negative slope to 0 slope. And now we'll keep moving. As we move forward, we see that the slope changes again. Look, so now as I keep moving to the right on the x-axis, my slope has to get increasingly steeper as I move. And so if I was going to plot in yet another point, okay, maybe right here, okay, I'll try x right here. If I go down to the function, put a little dot, and move my ruler in, I'm kind of forced by the limitations. I can't go above, I can't cut across the function. I've got to stay below the line, okay? Then I'm forced to draw something like this. So now I have a positive slope. It's kind of shallow, but it's still positive. Let's say I continue until I'm at whatever x value is over here by this, oops, hit the camera. Whenever the x value is right here. Okay, so what would I need to do with the ruler right here? Well, now I'm going to draw in a very steep positive slope. So look at what's happened. In this one quadratic function, we've got all these different slopes. So it's like it always changes. And so as a matter of fact, that's exactly what's going on. Every single point along this curve has a different slope. It's like a snowflake. You know, no two snowflakes are the same. This is like trillions of snowflakes, and every one of them is different, but they follow a pattern. Here we have a decreasing negative slope, decreasing negative until we get to this point, the vertex, and then the slope is 0. And then as we keep moving to the right, as we get more and more positive, the slope gradually increases as a positive slope until it gets to where it's darn near vertical. Okay, so what we say is the slope is decreasing as it moves toward the vertex, and then it begins to increase. And that makes visual sense. So that's the kind of visual background for what we're going to do here with mathematics. So this seems like a very reasonable question to ask in algebra. What is the rate of change of the function f of x equals x squared when x is 2, -3, and 0? So first, let's draw a little sketch. We'll sketch in the graph of f of x equals x squared. So let me draw this in. It's just a sketch, and it's not intended to be like a perfectly accurate rendering. Okay, and now we'll plot in our function using this blue pen. I'll use a colored pencil. We'll use this blue colored pencil. So x squared, when it's graphed, it's got the vertex is at 0, 0, and it moves out in an upward sloping fashion to the left and right. It curves up, I should say. So it looks kind of like this. And again, not something I would want to show an engineer, but it gets the point across. And this is f of x equals x squared. That's what's plotted right there. So what I would like to know is that these x values, let's mark them in somehow. And we'll label our function here. This will be 1. Okay, good enough. So this is 0, and this is 1, 2, 3, 4, 5. And this is -1, -2, -3, -4, -5. This is the x-axis. So far, haven't done anything weird. But now we just want to find out what the slope is. What you've learned how to do so far is evaluate functions at different values. So if I just stuck a 2 in right here, I would be finding the y value. So 2 squared is 4. Okay, -3 squared is 9. And it makes sense because what's happening on the y-axis is wherever I move away from 0, my y values are increasing. But that's not what we're after. We're not after the y value. We're after the slope. Okay, so I want to know what's going on with the rate of change, not the y value. I want to know what's going on with the slope. And because it's a quadratic function as opposed to a linear function, I can't just put it into y equals mx plus b form and tell you what the slope is at any given x value. I've got to do something, and that something is called take the derivative. So let me show you how to take a derivative. It's pretty simple. So here is how to take the derivative. This is a simple case, and it's something that everybody can do. Okay? So how to take the derivative. So your given function is f of x equals x squared. The way you take the derivative is to look at the exponent. It's 2. And you pull that exponent down right there. Okay? And so that becomes a 2 right there. you put a 2 right there, and that's multiplied by x, and then you come up to the exponent and you subtract 1. We'll do that again, because it's a very simple process, right? So just to make clear, the derivative, when we write that f prime, it's kind of like a little one quote or asterisk, not asterisk, apostrophe. F prime x equals 2 times x. And then the exponent 2 minus 1 is just 1. So the derivative of f of x equals x squared is just 2x. Let me show that again. So if I want to take the derivative f prime x of x squared, what I do is I pull down the exponent and put it right here in front of the x, and then I subtract 1. Now just do it one more time. Take the derivative of the function f prime of x squared, okay? F prime of x squared is equal to 2x. Bring down the 2 and subtract 1 from the exponent. Okay, so now that we have the derivative, let's use it. So do you notice that this derivative right here is a linear equation? It's a linear term. So now we can actually evaluate that derivative. F prime x equals 2x. So the derivative of x squared is 2x. And let's evaluate it at some x values. It says, what about when x is 2? What about when x is negative 3? What about when x is 0? So we'll make a little table. So this is the x value column, and this is the f prime x column. So the first one was 2. So when x equals 2, what is f prime x? Okay. In other words, when x equals 2, what is the slope of the quadratic function? Well, it's 2 times 2. We just plug it in, right? 2 times 2, and that's 4. So at x equals 2, the slope of the function is 4. How about when x equals negative 3? Now, what do we anticipate it will be? What is the slope when x equals negative 3? Let's go over here. We'll use our ruler to kind of move it in. So I know I can't come in like this because I can't cut across the picture. So I start over here, moving, turning this ruler the whole time until I get over to where x is negative 3. So I'm anticipating that I'll have a fairly steep negative slope. See that? Just using the ruler, you can tell you're going to have a fairly steep negative slope. So let's do that. Let's see what the derivative tells us. I know I'm going to put 2 times whatever x is, in this case, negative 3. 2 times negative 3 equals negative 6. Okay, these are slope values. So this is the slope at x equals 2. It's 4. The slope at x equals negative 3 is negative 6. Okay, so that's how you interpret the output. And now we'll try the last one. How about when x equals 0? And remember, this is a special point on the graph because 0 is the vertex. So what do we anticipate it will be? Come in here with your ruler. Okay, by the time you get to that lowest point, you see that your ruler is perfectly horizontal. So the slope of the ruler is 0. So we anticipate it would be 0. So let's evaluate f prime x at 0. So that would be 2 times 0 equals 2 times 0 is 0. So that's confirmation, right? The slope at the vertex, or the slope at x equals 0, is just 0. Okay? So if I was going to draw those slope lines in, I would draw in over here at positive 2. I'll draw in, we'll use red for this one. I'll draw in at positive 2. What I do is I take my ruler and I go up to the curve right there. So right there at that point on the curve, my slope is 4. Okay, I'm trying to guesstimate what that looks like. Okay, there, my slope is 4. At x equals negative 3, and we'll use the orange, at x equals negative 3, let's go over to x equals negative 3 and move up to the curve. Okay, so right there, I want to know what's going on with the slope, and it says the slope is negative 6. So I should have an even steeper line right here, a negative slope. Okay, so the slope there is negative 6. Then I come over here to the vertex of the function at x equals 0, and it says my slope is 0. Use green. Okay, at 0, I have to come in here and draw a 0 slope. Okay, so that's what this is useful for. Let's do another example. Okay, we might return and take a look at what we just did, but let's do another example. Right? Let's see, what is the rate of change? All right, here's another example. What is the rate of change, which we know is slope? What is the rate of change of f of x equals, we'll come up with a more interesting example here. We'll say 3x squared plus 2x plus 5. Okay? 3x squared plus 2x plus 5. What is the rate of change of this quadratic function when x equals 4, when x equals 0, and when x equals negative 7. Okay, we'll evaluate that. Drawing in that function would require us to figure out how to actually graph it 3x squared plus 2x plus 5. Let me just bounce away for 1 second. And 3x squared plus 2x plus 5. I'm going to use Desmos to just graph that real quick. Graph 3x squared plus 2x plus 5, just so we know what it kind of looks like, so I can sketch it. Okay. Okay, so here's what it kind of looks like. Draw the graph over here. So this is y, and this is x, and this is 0. And my graph, let's see here. Okay. What we'll do is we'll make a bigger demarcation. So this will be 1, okay, and then this will be 2. So this is -1, -2, and this will be 1 and 2. So this is 1, 2. Okay, so what the graph looks like is something like this. It looks like this. About like that. Okay, so that's what f of x equals 3x squared plus 2x plus 5. That's what that is. Looks like graphed. So now let's take the derivative of this function. And let me show you how easy this really is. So remember the rule. Whatever the exponent is, you bring it down. Okay? And when we bring that exponent down, we have to multiply it by whatever's sitting there. And then we subtract 1 from the exponent. Over here, we'll do the same thing. This has an exponent of 1. And this 5 has an exponent of 1. So we'll see what we put there. Okay, so here we go. Let's take f prime x. F prime x equals, follow the process. You take the exponent, so I've got 3 times, bring down the 2, like that. 3 times 2, x, and then subtract 1 from the exponent. 2 minus 1 is 1, so 3 times 2x is going to be 6x, plus, now, what is 2, got 2x plus 2, and then x to the what? So it's right now it's x to the 1, and so I'll subtract 1 from the exponent. Now I have x to the 0. So what is x raised to the 0 power? It is just 1. So x to the 0th power. This is x to the 1st power. And this is x to the 0th power. Now what's going on with the 5? In derivatives, if you have a number like this and you take the derivative of it, it turns into a 0. Okay, so these whole numbers just disappear. They just disappear entirely. So 5 just disappears and becomes nothing. It's a 0. Now let's clean this up. So f prime. So in other words, the derivative of f of x is equal to 6x plus 2, because this becomes a 1, 2. 6x plus 2. So now that I've found that derivative, I can now find out what the slope is at various x values on this curve. And you can't do that without this little handy piece of technology called the derivative. Okay? I just want to point out that this gives us the slope. Okay? Or the rate of change. That's what this thing is giving us. So you put in an x value and it outputs the slope. Okay? So let me just let me write this another way just so it sinks in. The input to this derivative, input an x value. You input an x, and you put it inside the little machine called the derivative. And the output is a slope. That's what is going on here, functionally. Okay? So now let's evaluate our derivative, make our little table. So here's my x value, and this is my derivative, f prime x. Keep saying prime. F prime x means the derivative of the function f of x with respect to x. But it's the terminology gets confusing, so you just put in the numbers and see what you get. You put in a 4, and now you're going to plug the 4 into this right here. So you got 6 times 4 plus 2. And what does that equal? 6 times 4 is 24, plus 2 is 26. So to write this out in English, the slope of 3x squared plus 2x plus 5 when x is 4 is, so the slope of 3x squared plus 2x plus 5 when x is 4, the slope is 26. So that's extremely steep, and it's a positive slope. So that's a positive number. If we were going to draw that in, we would have to keep going with our little scale. Put in 3 here, and 4 would be right there. Somewhere way up here, if you think about this function, look, just think about this. So I'm going to continue this graph out. So it just keeps going. Let's see if I can make it look good. It keeps going, right? And going and going. And so by the time x is 4, look at what I'm doing with the ruler. It's almost perfectly vertical, right? So right there, the slope, and I'm going to have to, the slope is 26. So it's extremely, almost vertical, almost vertical. Okay, so let's ask another question. What is the slope of this quadratic when x is 0? Now let's guesstimate it. So we move down from 26, coming down, coming down, coming down, coming down to where x is 0. Now notice something. The The vertex of the function is actually located right here. So we know that we're going to have a very shallow positive slope at x equals 0, but we know it's not going to be 0. It's going to be something greater than 0. So that's what we're anticipating. So let's evaluate it. 6 times 0 plus 2. Well, 6 times 0 is 0, plus 2 is 2. So that's just 2. So let's write that out. The slope is 2, the slope being the m value, right? The slope is 2 when x is 0. That's interesting. Now let's look at -7. So now we're going way, way, way out here, somewhere over here. Okay, it would be impossible. In order for me to show you where the graph would be, it would be way off the page. I'd have to draw a line like 6 feet long. So we're going way over off the graph at -7. So the x value is -7. What are we expecting? Well, if we travel along the curve, we're expecting this thing to be a huge negative number, right? A huge negative slope. Very negative is what we're expecting. Look, at x equals +4, this thing was the slope was 26. So at x equals -7, it should be even bigger than 26, but negative, right? So something negative that's even bigger than 26. So let's do that. Now that's 6 times -7 plus 2. Well, 6 times -7 is -42 plus 2. So -42 plus 2 is -40. So this equals -40. That's the slope. Okay. So the slope of f of x at x equals -7 is -40. Okay. So an interesting question is, where's the vertex? Okay. So if we were going to solve for the vertex of the function, we would need to do a little bit of gymnastics. But the vertex of this function is 1/3. Okay. So let's evaluate x at 1/3 and make sure that the math works. So what do we anticipate it to be? At that vertex, oops, I meant -1/3. Okay, the vertex is at -1/3, right here, -1/3. So when x is -1/3, what do I think my slope is going to be? I think it's going to be 0, all right? So let's plug it in. 6 times -1/3 plus 2. Well, let's think about this. I've got -6/3. So I have -6/3 plus 2. Well, -6 divided by 3 is -2. So I got -2 plus 2. -2 plus 2 equals 0. So the slope at x equals -1/3 is 0, because x equals -1/3 is the vertex. So the slope's always 0 at the vertex. That's something we've learned today. Okay, well, this was just a little introduction to what does the derivative help me do? The derivative helps me find the slope. Okay? So question, answer. The derivative, it helps me find the slope. And how do we take the derivative? That's another question. How do I take the derivative? Well, remember, the method for taking the derivative. Got f of x equals 6x squared plus 3x plus 193. The derivative f prime x is equal to, bring down the 2, it's 6 times 2, okay, and then you've got x to the 2 minus 1. You always subtract 1 from the exponent. Plus, okay, this one has an exponent of 1, so here we brought the 2 down. Now here we're going to bring the 1 down. Okay? And so we bring down the 1, and now I've just got 3 times 1 times x. And we drop the last term. The constant term disappears entirely. All right? So this and this x becomes 1 minus 1. So, and then that constant term, 193, just becomes a 0. Okay, so let's finish that one out. So that's 6 times 2, that's 12x. And then 2 minus 1 is just 1, so it's just 12x. Plus 3, 3 times 1 is 3. And then x to the 1 minus 1 is x to the 0, and that's just 1. So the derivative is f prime x equals 12x plus 3. So that's the process. You bring down, the process is bring down the exponent, then subtract 1 from the original exponent. That's the process. So now you have learned how to take the derivative, and you've learned what it can help you do. The derivative can help you find the slope of curved lines. I should add that. It helps me find the slope of curved lines. Because with curved lines, the slope constantly changes. You see that? The slope constantly changes. So I've got to use the derivative to find the slope of curved lines. All right, thank you very much for watching this video, and I hope that you found it somewhat useful. If you have any questions about this video, please leave a question in the comments section. Okay. Please like and subscribe, and hit that notification bell to be alerted every time we have a new video. Thank you very much.